Welcome to the brand new section of this course, Building Models with Distance Metrics. In this section, we will look at clustering, optimizing and assessing, handling data and quantizing an image, finding the closest object in the feature space, probabilistic clustering and Gaussian mixture models, using k-means for outlier detection, using KNN for regression. Now let's move on to the video, clustering, optimizing and assessing. In this video, we will start with using k-means to cluster data, then optimizing the number of centroids, and finally, assessing cluster correctness. Let's start with using k-means to cluster data. With k-means, we will categorize all the points into groups or clusters. First, let's walk through some simple clustering. Import libraries. Then generate isotropic Gaussian blobs for clustering. The number of centers to generate, or the fixed center locations. Also, since we'll be doing some plotting, import matplotlib as shown. Now it's time to visualize the plot, so use this command to visualize scatterplot with the title as blobs. We're going to walk through a simple example that clusters blobs of fake data. Then we'll see how k-means works to find the optimal number of blobs. Let's run it and use plot.show command to see the graphical representation of it. Looking at our blobs, we can see that there are three distinct clusters. Post that, we can use k-means to find the centers of these clusters. Import k-means from scikit-learn.cluster. So, in this example, we'll pretend we know that there are three centers. The number of clusters to form and number of centers to generate is 3. After that, we fit the blobs with kmean.fit command. Next, we will check the coordinates of the center with typing kmean.clusterCenters. Run it, and you will get the array as highlighted here. Use the highlighted art to add the subplot with the title as blobs and LOC as best, which will set the best location for our graph. So it's time to use plot.show command. Nice, here is the plot that we were expecting. Other attributes are useful too. For instance, the kmean.labels will produce the expected label for each point. Run it and you should get the array as highlighted here. We can check whether kmean.labels is the same as the classes, but because k-means has no knowledge of the classes going in, it cannot assign the sample index values to both classes. Use this command. Run it and you will get the array as shown here. Feel free to swap 1 and 0 in classes to check whether it matches up with the labels. The transform function is quite useful in the sense that it will output the distance between each point and the centroid. Use kmeans.transform command. Now we can run this and here is the output array. Next we will see optimizing the number of centroids. When doing k-means clustering, we really do not know the right number of clusters in advance, so finding this out is an important step. Once we know or estimate the number of centroids, the problem will start to look more like a classification one, as our knowledge to work with will have increased substantially. To get started, we'll create several blobs that can be used to simulate clusters of data. For that, we will import makeblobs and numpy. Use kmean.fit to fit the k-means cluster with value 3. Run it and you should get the output as shown here. After that, we'll look at the silhouette distance. Silhouette distance is the ratio of the difference between the in-cluster dissimilarity and the closest out-of-cluster dissimilarity, and the maximum of these two values. It can be thought of as a measure of how separate the clusters are. Let's look at the distribution of distances from the points to the cluster centers with the help of these commands. This will compute the silhouette coefficients for each sample, and this will stack 1D array as columns into 2D array. Let's run it and you would get the output array as highlighted here. With the help of this command, we will get the average of the silhouette coefficients that is often used to describe the entire model's fit. Run it and you will get the array as shown. It's very common. In fact, the metrics module exposes a function to arrive at the value we just got. So next, we will check the silhouette score with the help of this command. Following that, we will visualize it. For that, we will import matplotlib as plt. We will create several blobs with this command. Number of centers are 10 to generate or fix center location. After that, use this for loop and array will get the silhouette average. Post that, we will use this command to plot the silhouette in the form of graph. So it's time to run it. Cool, this is the output. This plot shows the silhouette averages as the number of centroids increase. We can see that the optimum number, according to the data generating process, is 3. But here it looks like it's around 7 or 8. This is the reality of clustering. Quite often, we won't get the correct number of clusters. We can only really hope to estimate the number of clusters to some approximation. Finally, we will be looking at the assessing cluster correctness. We'll create a simple dataset, evaluate the measures of correctness against the ground truth in several ways. After creating that, we will import matplotlib.pyplot and visualize the content with the title as cluster with ground truth with the help of these commands. So it's time to run and check the graph. Cool, here is the graph. In order to fit a k-means model, we'll create a k-means object from the cluster module. So for that, first fit the blobs and run it. Then use k-means.cluster centers to check the centers of the cluster. After running it, we should get the array output as highlighted. Now let's have a look at the cluster centroids. Run it, and you should get the output as shown here. Now that we can view the clustering performance as a classification exercise, the metrics that are useful in this context are also useful here. So let's check the output. Here I have highlighted the array output. Clearly, we have some backward clusters. So let's get this straightened out first, and then we'll look at the accuracy. So we're roughly correct 90% of the time. We'll look at is the mutual information score. After running, we would get the output around 1. As the score tends to be 0, the label assignments are probably not generated through similar processes. However, a score closer to 1 means that there is a large amount of agreement between the two labels. For example, let's look at what happens when the mutual information score itself. Given the name, we can tell that there is probably an unnormalized mutual info score. Using this command, run it and you would get the output around the highlighted values shown. These are very close. However, normalized mutual information is the mutual information divided by the root of the product of the entropy of each set truth and assigned label. Finally, we will see the inertia, which is the cluster metrics. It is not very well documented as a metric at the moment. However, it is a metric that k-means minimizes. Inertia is the sum of the squared difference between each point and its assigned cluster. We can use a byte of numpy to determine this. Use k-means.inertia command. Run it, and you would get the output as highlighted here. With this, we end our video.